In this video, we're going to evaluate definite integrals that involve a u-substitution. Before you watch this video, you should have already found the solutions to indefinite integrals that involve u-substitution. So you should already be familiar with the technique of u-substitution. So the example that we're going to do today is this one. So when we look at this problem, remember, when you're doing an integration problem, you always want to see if you recognize the antiderivative first. In other words, is there a function that we can take the derivative of that results in this integrand? I don't think there is. However, if you look at just the secant squared piece, we know the derivative of tangent is secant squared, and we have a tangent right here. So a nice u-substitution here is to let u equal tangent x. If we let u equal tangent x, then our du is going to be secant squared x dx, which provides a nice substitution for this particular problem. So let's go ahead and do that. When you do the substitution, you end up with u du. Now you have to be careful. Remember, these are x values. So you can't just copy these limits of integration down. You actually have to plug these into the x here and see what you get out. Well, the tangent of 0 is 0, so this becomes a 0 down here, and now it's a u value. And the tangent of pi over 3 is the square root of 3. If you've forgotten that, you might want to draw yourself your right triangle here, which is going to be a 1, 2, square root of 3 triangle, because this is a pi over 3 angle or a 60-degree angle, and you can see that the tangent of that angle, pi over 3, results in opposite over adjacent, which is square root of 3 over 1. Alright, so that's where that comes from. Now that we have this figured out, we can take the antiderivative and then we can evaluate. So our final answer should be 3/2. So when you're evaluating the definite integral, what I like to do is go to the u's, and since you can turn these limits of integration into u's, you don't need to go back to the x's. So this is a little more efficient than substituting back for the x's. However, if you want to substitute back into the x's, you can definitely do that. So let's say that we ignored these limits of integration here. We ended up with our antiderivative and we substituted the tangent of x back in. You could also have done it this way. If you solve the problem in this way, you should end up with the same result, but it actually seems like it might be a little more work. So there are two ways to do these problems. We're going to do 2 more examples, so after you've copied this into your notes, make sure you watch the next 2 examples.